There's been a lot of excitement surrounding quantum computing. So in this video, we're going to provide a little bit of an introduction as well as describe some applications that quantum computers are proposed to be really good at. First, I want to highlight though, that classical computing is everywhere. This classical computing paradigm is seen in everything from laptops to cell phones, supercomputers, etc. And what powers these devices are different types of software, like operating systems, apps, web browsers, etc. So if we have all this computing power available to us, why would we even need a quantum computer? Well, that's because we have limitations on our classical computation. Classical computers are really good at solving many day-to-day problems, such as algebra and calculus, and they can do so faster than a human. But there are still many complex problems that are intractable. So what does intractable mean exactly? That means that we need an infinite or a lot of resources or time to solve these problems. So some examples of these types of problems include natural processes, and finding a solution when there might be an exponentially large set of potential solutions. One particular example of this type of problem is chemistry simulation. So chemistry simulation is a modeling of a natural process as well as trying to find a solution in a state space where there are many different types of possible solutions. So whenever we think about chemistry simulation, that can involve simulation of molecules, and it can be applied to develop improved chemicals and materials, such as pharmaceuticals or fertilizers. So classical simulation techniques for chemistry are implemented with a sort of guess and check type of mechanism. So in this kind of process, theorists will develop hypotheses. We'll have experiments that are outlined and performed. And then these results are analyzed. And then with those results, we develop new theories. So the efficient simulation of atoms and simple molecules is one of these things that we suspect that near-term quantum computers are going to be really, really good at. So we can look at an example of this. Classical computers have a really difficult time representing information associated with chemical bonds. And that's because all of the components in a molecule, in a way, feel each other. So if you adjust one placement of one of those particles, all of the rest are impacted. So that creates many, many different variations that can exist with how the structure of the molecule is set up. So molecules, of course, have protons, neutrons, electrons, and these can all be organized in different variations of configurations. So caffeine, pictured here, is simply a 24 atom molecule, but we would need 10 to the 48 bits to represent that. And that's a lot. All the possible different energy arrangements would equal quite a lot of information to represent in the classical computer, so it's intractable. However, a quantum computer could hold all this information in 160 qubits, which is a lot less than 10 to the 48 bits. Another proposed application for quantum computers would be optimization problems. So optimization problems fall into that category of problems that have a very, very large state space for the answers that are possible. So when we think of optimization, we can try to maximize resources in terms of time, energy, hardware. And one example of this is the fact that UPS optimizes its routes for minimal left turns rather than shortest route. So because of this, it's able to save 10 million gallons of fuel each year and deliver 350,000 more packages. So that's pretty significant. So classical optimization involves really computationally expensive types of search algorithms. And most of the time we can't even find the best, we just have to find a good enough solution out of all the potential solutions. So because quantum computers are good at exploring large state spaces, they're anticipated to be really good at finding optimum solutions for these types of optimization problems. So let's kind of dig a little deeper into that. An example application for quantum computers would be a optimization problem known as the traveling salesman problem. So the traveling salesman problem is a problem that aims to find the shortest route in a round trip journey. So here we have a picture of a tour of Italy, and we have the optimum route outlined here. So we want to try to find the route where we travel the shortest amount of distance possible. And that can get to be quite a lot of different variations of the journey as we include more cities in our trip. So let's look at this. If we have 20 cities that we're visiting, we actually implement a factorial all the way down to 20 times 19 times 18, all the way down to 1. And that creates a very, very large number of combinations for the possible journeys that we can take. So quantum computers model optimization in such a way that qubit optimization or qubit observation has a high probability of determining the best route without having to check each single one. So that's done through the simple procedure of defining a target solution and defining the cost, encoding qubits with our search equation, and then allowing those qubit values to converge to the ideal route in relatively few number of iterations. So to kind of summarize some of the applications that quantum computers are targeted to be really good at, we have chemistry applications such as battery material discovery, fertilizer production, drug discovery, material durability. We have optimization problems, so financial market analysis, manufacturing applications, and then transportation optimization as well. Security applications, so we have more robust encryption schemes and more secure key generation are some examples of ways that we can apply quantum computing to security. And then of course, machine learning. We can apply quantum computers in applications potentially for artificial intelligence, audio and image generation, and predictive models. So let's look a little bit more into what the difference between a classical and quantum computer is physically. So we look here, to the left, we have the Summit supercomputer, and to the right, we have a UChicago quantum computer. So here we have around 250 times 10 to the 15 bytes of storage. That's a lot of storage. Compared to the tens of qubits of storage on the Schuster quantum computer. So although the quantum computer is a lot smaller in terms of number of fundamental units it includes, so we have the qubit over to the right on the quantum computer rather than the bit on the left with the classical computer, we have a lot of benefits in the way that we encode information that allows us to get those speed ups with our certain types of computation. So moving forward with quantum machines, we need to make them more robust, more reliable, and generally scale them so that we can implement these different types of algorithms for optimization, for simulation of natural processes, and for security purposes. So there's many technical challenges that exist currently with scaling these machines in the terms of number of qubits. And that's because we have relatively short lifetimes and they're very error prone. They're very willing to communicate not only with each other, but the surrounding environment. So we want to make sure that we make them more robust from interactions outside of their computation. So we have these devices that are currently very sensitive, and we have limitations due to hardware and software. So we need to have more of these, not only more qubits, but more connections between these qubits. Finally, we also need to think about improving the control and hardware that will allow for more sophisticated systems and algorithms. We just have a couple of applications that we've outlined here, but there's a lot more potential to discover new applications, especially as these devices become a lot more robust, reliable, and increase in size. So some takeaways. Quantum computing is projected to be revolutionary and can potentially drastically change the way we solve some of the most challenging problems that exist for us today. So in this course, we'll learn a little bit more about why quantum information is different from classical information and how it potentially can change the world.